Metamaterials are engineered materials designed to have properties that are not found in nature. Their defining feature is their structure, which is crafted at scales so much smaller than the wavelength of light or other waves that they interact with. And this allows them to control and manipulate wave behavior in extraordinary ways. One of the most remarkable phenomena metamaterials enable is negative refraction. Normally, when light passes from one material to another, like air to water, it bends or refracts. It happens right at the boundary. This bending follows Snell's law, dictating that the angle of refraction depends on the material's refractive index. Metamaterials break this rule by having negative refractive index, meaning that they bend light in the opposite direction of natural materials. This property opens doors to a host of groundbreaking applications. One of the primary thoughts is invisibility cloaks. By guiding light around an object instead of reflecting or absorbing it, metamaterials can render the object effectively invisible. This principle is called optical cloaking. While it's claimed to be in experimental stages, prototypes have been proven to work for specific wavelengths of light. So is it possible it might not be an experiment anymore? Who knows? Then there's superlenses. Traditional lenses are limited by the wavelength of light, a constraint known as the diffraction limit. Metamaterials overcome this, creating lenses capable of focusing light to much smaller points, enabling imaging and resolution at a far beyond conventional optics scale. This is transformative for fields like microscopy and medical imaging. Then there's wave manipulation. Beyond light, metamaterials can control other types of waves, such as sound or electromagnetic waves. This is leading to innovations like noise-canceling structures, better antenna designs, and even earthquake-resistant buildings. At the heart of this technology is precise structural engineering. For instance, researchers create arrays of tiny repeating patterns, like rings or spirals crafted from metals or dielectrics. These patterns interact with incoming waves, altering their speed, direction, or energy in specific and very controlled ways. There are primary challenges that remain, though. Metamaterials often work only with narrow frequency ranges and are difficult and costly to manufacture. Scientists are now exploring 3D printing and nanofabrication to scale production and expand their practical uses. So this is not science fiction. Scientists are literally rewriting the rules of physics, creating tools that seem magical, but they're deeply rooted in precise engineering and the manipulation of wave phenomena. These are Interesting Things with JC.